Homework, I graded a couple of these mainly so that you and I both have an idea of where you are. So most people did well on it. A few people did okay, and some people really had problems with it. If you didn't do well on this, my first piece of advice is to change somehow how you're doing the homework. In other words, if you haven't been going to office hours, you need to go to office hours. I'll be at mine now, and of course, you have James's office hours to go to. There's a hurdle that happens right at the beginning of learning this stuff, and the hurdle is, and this is going to sound strange, is learning what it means to understand mathematics. Okay, and because previously understanding mathematics may have meant to you, that you learned some steps to solve certain problems, and this is very, very different. But in some senses, but the underlying core is the same. That is, you have to learn some very precise things. They're just different from what you had to learn before. Right, and I'll keep going through these, but there is no sort of algorithm. I can't teach you to do proofs. All I can do is help you through proofs and give you hints in office hours or by email about how to do proofs. And your job has to be to go through and read these things carefully and wait for that time where suddenly things start to click a little bit. And that's the only way I can describe it. It happens to most students in here. Some of you have already clicked. There are other hurdles coming later, okay? So don't rest on your laurels. But sometimes it takes, some time to figure out what's happening here. It's, like I said, sometimes the brain isn't really ready for it yet, and you need a little wiring, and that's hard work, right? That's hard practice. Okay, so keep working at it. So you're Jonathan. Okay. All right. So along this line, and also another thing you can do is ask questions in class when we're going through. Right now, I'm sure James didn't. I'm going to proceed what later will seem like a very slow pace. Okay, we'll pick things up later as things start to click. But you need to watch for certain things when you're starting a proof. Make sure you know what you're proving. Okay. Now I know that sounds kind of silly. Well, yeah, of course I know what but in many cases, and when I look at these papers, you actually don't know what you're proving. Those of you who didn't do well. You're trying to prove the converse. You're getting your assumptions mixed up. And just taking a few minutes at the beginning of the problem to think carefully about what in the world is it I'm doing. And what is the opening line for the proof? Once you know what it is you're proving, then a lot of these have an opening line, and it's mentioned in the book, and I'm sure James talked about this. And if you can just get that without even worrying about how you're going to do it, just start by thinking about what in the world you're going to do. And then, start from the beginning, and your strategy should be, for starting, should be dictated by the thing you're trying to prove. Okay. Later it gets more complicated because you have to choose between various theorems that might be useful. You even saw that in calculus when you're doing integrals or something. You had to sit and think about which kind of method would apply in a particular case. All right. So it will get more complicated, but for now the whole idea is just to get you to the point where you know what a proof is, you know how to locate what it is you're trying to prove, you know how to get started, and then you know how to sort of follow your way through the definitions to the other end. That's really at the stage we're at right now. So last time, James tells me you were working on this problem. Here, okay, and he and I may use slightly different notation, but that's actually healthy, right? Some texts, including Dr. Wade's text, if any of you have ever seen that one, likes to put an equal there. That's just an extra pain to do it in LaTeX, which is what I write this in. And some texts do this and some do the other way. But anyway, that's actually good, right? It's sort of like learning synonyms in English to improve your ability to write. Okay, and so the one that I believe he now left off from the last one is going in this direction. Okay, does everybody understand? Now this means equivalence, right? And everybody understand actually not only what that symbol means, but really what the whole thing means. It means that if you know this, then you automatically get that for free, right? That's what we're doing now. A proof is a way to sort of help you get things that you need later, okay? Or if you know that, then you automatically get that for free. These two are equivalent statements. All right, and the idea is at some point if you're doing a more complicated proof later and you're trying to get that and you're going along and then you reach this, you can say, ah, I'm done, because there was an exercise earlier that said that if I have this, then I have that. Okay, so that's the whole idea. And in mathematics, you build these things up. And so you have two things. You have to know and understand your little theorems and proofs and exercises. You have to remember all those things. But they also have to make sense to you. And the way they make sense is by going through the proof and being able to prove them. Okay, so now let's think about, again, let's back up and look at this. Okay, the implication is this way. So what is it we're assuming here for this? This pen is getting a little dry. I'm going to try something else. What are we assuming now? I'm going to just write it out and be very explicit right now.
A take away B is equal to the empty set.
Yeah, so we're assuming this. And again, I mean, if you're struggling with this, you know, if you're not making, you know, 7 or 8 or 9 or 10 on your homework problems, then this is what you need to start doing, okay? Actually explicitly write down what is your assumption. Okay, and then what are we going to prove now? And really write down the word prove, right? Because then in your mind, you're thinking, okay, this is what I'm after, so you know where to start. So what are we proving in this case? And go ahead and say it, okay? Even though, you know, you may think it's obvious, just say it. I mean, I don't need hands up or anything like that. What are we proving? I mean, you don't want to say it because you say, well, it's right there, so why doesn't it just write it down? Okay, but you know, right? We're trying to prove this, right? A is a subset of B. Okay, that's what we're trying to prove. Okay, now forget everything except that. Okay, just forget what you're trying to, you know, how are you going to do it? Just think about that to get started. Okay, and there is an opening line for that. And what is it? It starts with L, yes, let, okay, right? And this is, there are some things that you can just learn as things that you always do, okay? And, you know, one of them, you know, you can never go wrong if you're trying to prove this by starting with let X be an element of A. Right? And if you don't write that down, you're not going to have a proof. Because you can't start anywhere else. There's no other way to start this. And this is what I say by sort of, you know, write down what you know and then sort of follow your nose through it, right? I mean, there's no other way to do this. And if you realize that, then it's immediate. You see this and your brain says, okay, write that down. And then you start thinking, okay, now what is it I have to prove? So you go back and look at what you're trying to prove about this. So what's the last line that you have to get? When you're all the way done, what is your conclusion supposed to be?
A is a subset of B.
Okay, back up, okay. You've picked up this X, okay. You're right, that's where we're headed. But now we've got this X. So what do I have to show about X?
X is in B.
Yeah, right? I mean, this is what I'm headed for. And that's why we define all these things, intersections, unions, and all that, not by this picture. Remember the and or weirdness, right? Okay? We define them by the properties of some X that's in there. So when you say let X be an element of A, hey, I've got an X here. Now, what do I do with it? Okay? Well, what I want to do with it is show that it's in B. Okay? So again, all this can be done without even thinking about how you're going to do it. Right? And so if you're still struggling with this, go ahead and write your opening line and then decide what you're going to do, where you end up. And you can sometimes even, and this works even when you're doing really hard proofs, right, later, that you can sometimes kind of start at the beginning and start at the end and work your way, you know, go backwards a little bit, go forwards a little bit, and you have to be real careful with your logic, okay, right? Because your logic has to go one way, so you really have to be going backwards with your logic if you're starting from the end, all right? But okay, now we've got this. This is what we want to show. Okay, now we've got to figure out how to fill in the empty space there, right? And we have only one piece of information, and that's this guy right here, okay? So think about what that means, right? For this to be empty, that means there's nothing that satisfies this, right? Okay, so, and this means that what? X is
An element of A.
and?
And
and not an element of B. Okay, so that should be triggering something here because you're trying to get that X is an element of B, and this has a not in it. So this might suggest how might be a good way to actually proceed here.
Just say by definition.
Well, by definition, what?
A take away B.
Okay, but you've got this X, and you've got to do something with X.
Definition, X is an element of A and not an element.
How do you know it's not an element of B? X is, all you know about X is that it's sitting there in A.
We want to show that.
You want to show that it's in B, so you got to do something with this guy. Now, there are two basic ways to prove things, right? What are they? It's directly and by contradiction. Okay? Now, since this thing involves a not, I mean, this is how you sort of think about these things, right? Okay, well, maybe then let's try to prove it by contradiction. And if I'm proving it by contradiction, what's my next line?
Suppose X not.
Right, so let's suppose X is not an element of B. And now is where your definition comes in, right? Because what have I just written down? Where is X at this point? X is in A and X is not in B. So where does that put X?
A supposes B.
It puts it in A take away B, and what do we know about A take away B? It's empty. It can't have anything in it. So that's our contradiction. Okay? Now, if you got all this, great. If you're ahead of me, that's great. Okay? If you're still struggling with this, you've got to go back and take this exact same problem and work through it. If you're still struggling, come to office hours, take this exact same problem and work through it. And build up, you know, the wiring that you need to become instinctive about where to go. Okay, so let's finish writing this down. So then, by definition, X is an element of A take away B, and that's a contradiction. So this is, I don't know whether James used this or not, but that's contradiction. And if you want to say what the contradiction is explicitly, it contradicts the fact that A take away B is equal to the empty set. Okay, so just a general idea here. So when using, well, let's put it this way. When proving things, involving, and this isn't always true, but I'm going to say, consider proof by contradiction. Why? Because the empty set is empty. There's nothing in it to get your hands on, okay? Whereas if you work on proving something by contradiction, so for example, if you're trying to show something is empty, and I think you've been through some of these proofs already, when you prove it by contradiction, you're saying let X be in this set that you're supposed to be showing is empty, and then you got some X that you can work with, right? It's better than having nothing. And what's nice about a proof by contradiction is it often can be used in a situation where you don't seem to have anything, like here, and then it gives you something to work with. In fact, one thing I've discovered after teaching this course many times is that a lot of the students who are really getting it, they actually use proof by contradiction almost too much. Okay, and I've never complained about that. I'm just commenting on that, right? Because it's fine as long as it's correct. I don't care, you know, which way you do it or about, you know, mathematical etiquette or anything else. But you know, often. And so what does that tell me? That tells me that student, the reason they're doing well is that they're trying different possibilities in their mind. They're trying proof by contradiction or direct proof, and so they're sort of trying different directions, and that's how you do these things, right? You have to be thinking about lots of possibilities. But the first thing you got to do is get started, okay? You got to get started. Know what it is you're proving, know what it is you're starting with, and then write down your opening line for your proof. Okay? And when you're done, again, if you're still not doing well, when you're done, go back and look what you wrote down and double check. Did you actually prove what you're supposed to prove? And you know, everybody makes mistakes, right? I make mistakes, all of you will make mistakes. It's impossible to do mathematics very long or at a very high level without making mistakes, okay? And the difference between somebody who understands and someone who doesn't is that when somebody who understands makes a mistake, it still makes sense, right? I can get there and I can say, well, here's the mistake, and they're, oh yeah, right, I screwed up, okay? So, and you know, if I make a mistake up there, somebody will point it out and yeah, it'll be clear, right? But someone who doesn't understand, there's nothing to get a handle on because they're not starting in the right place, they've got the assumptions mixed up and everything, and it's just really, okay? And so, you know, if I haven't pointed out some clear mistake in what you've done and you didn't get full credit, and especially if your grade is below 5 on a particular problem, that means that I can't make head or tail of it, and you need to really get back and focus on the definitions and starting point and all of that. And by all means, bring those by and we can talk about it, right? Or James can talk about it. Okay, any questions about this? Yes?
So are we going to finish this? Or
We are. Okay, we can put the therefore there if you want. We are finished because, right, we suppose x is not equal to b and we got a contradiction. And since we got a contradiction, this assumption was wrong, meaning it must be true that x is in b.
Okay.
Okay?
So we've proven that x is an element of A and x is an element of B. So
No, careful. And this is a common mistake when you're proving something's a subset, okay? You're not trying to prove x is an element of A and x is an element of B. You're trying to prove if x is an element of A, then x is an element of B.
but it looks
Okay? And that's different from an and statement. So be very careful. And I do see this a lot in homework in the early stages, right? What you're proving, so you assume that x is an element of B, that's the let statement, right? And you want to wind up here. So what did we do? We assumed it wasn't in B, that was the proof by contradiction, right? And then we just wrote out the definition and found that, well, x is in this thing that's supposed to be empty. And that was our contradiction. Since we got a contradiction, this thing we supposed right here is not true. If that's not true, that means that its negation is true.
To me, it looks like we've proven that x is an element of A and x is an element of B. But I understand that it's not the same as the subset. So how do we get to the subset?
Okay, so when you're done with this, it is true that x is an element of A and x is an element of B. Okay, but that's not what, I mean, so you can reach other conclusions, right, from a proof. Okay, so this also proves that x is an element of A and x is an element of B. But that's not what we set out to do. Okay? Does that, right? I mean, it sounds like you want to conclude something else, which is okay, but what we're after here is that if x is in A, we want to show that it's also in B. And when you're done with that, it is in A and it is in B. But that's not the framework. Okay?
I mean, if it's in A and it's in B, does that mean we've proved A is a subset of B?
What's your starting point for x?
X is an element of A.
Okay. And once you're at that point, if you show it's in, if you then show it's in B, then you're done. Okay. What worries me about what you're saying, sometimes I have seen x sort of appearing from nowhere and then somehow concluding that it's in A and B, and that's not really what you're trying to show. Okay. So I mean, what we've done here, I mean, our goal is not, I mean, that's automatic, right? If you show that, if you pick up x and it's in A and you later show that it's in B, then it's true. It's in A intersect B, but actually, you know, A is sitting inside B, so that's not what we're after, actually.
So I think might see what he's trying to ask. You think, for you look at that and you see x is a set, x is in A and in B, not A is a subset of B, right?
Pretty much. It doesn't. I mean, it doesn't look like we've proven what we've set out to prove.
Yeah.
Okay.
He doesn't see how this proves that A is a set of B.
Okay, let's write down what this means, right? This means that if x is an element of A, then x is an element of B. Okay? So the way we start this is we pick up something that satisfies the hypothesis, namely we let x be an element of A, and then we eventually want to conclude that x is an element of B. Now if you look at the Venn diagram, once we're done showing that this is true, then certainly anything in A is also in B. That's just a consequence of A being a subset of B. And so that's not really what we're after at this point. We're after picking up something, right? If it's not true, then then there's something in A that's not in B. So what we're after is picking up anything, any arbitrary guy in X, in A, and showing that it's in B. Once you've done that, it's automatic that anything in A is also in B.
How does the proof distinguish from A as a subset of B instead of B as a subset of A?
Well, if you were going to prove B is a subset of A, which may not be true in this case, you would pick up an X an element of B and show it's in A. The distinction here is that since you're showing A is contained in B, you have to pick up something in A and show that it's automatically in B. Okay, so if it weren't true, you'd have a real hard time because you might pick up this X over here and you have no way of showing it's in B because it's actually not in B.
Takeaway is not commutative, so.
Definitely not. Definitely not. They're different sets. Just like negative, you can't, right? 5 minus 2 is not equal to 2 minus 5. Okay? More questions about this? I mean, these are the things we got to root out right now, because if we don't get at them now, or if you don't get at them now, then you're going to have trouble as things get more complicated. So let's do another, let's do a kind of a big thing called disjoint union lemma. It's a useful thing. It comes up a lot in mathematics. And it says the following. If A and B are sets, and there are two statements we want to get here. Number one is sort of the reason it's called the disjoint union lemma is that A union B is equal to A take away B union A intersect B union B take away A, and any two of the sets on the right are disjoint. Sorry?
Where it says if A and B are sets, comma, is it?
Oh, that's a then, yeah. You guys will get used to my... Okay, yes. Okay, so the first part says that the union of A and B is equal to A take away B, union A intersect B, union B take away A. And any two of the sets on the right are disjoint. So if you pick up any two of these guys, what is that saying? What does it mean to be disjoint?
Nothing in common.
They don't cross.
We got definitions. What does it mean in terms of our definitions for two sets to be...
Element of A is
No, we've got a very clear definition. Okay, so this already... Okay, if you have to look up this definition, you're not approaching this properly, okay? Everybody should have that definition on the tip of your tongue. And here's the reason. When you're doing a proof, if you don't have the definitions right there, accessible, then you can't tell when using the definition is the right idea. Okay? So when I ask you what does it mean for two sets to be disjoint, you should immediately say the intersection of those two sets is empty. Okay? And if that thought, some of you maybe just didn't want to speak up, but if that didn't pop into your mind immediately, you're not spending enough time getting the basic definitions down. Okay? And you will have more trouble following what I do, and you'll have great trouble actually doing proofs. Okay, so you shouldn't have to flip through your notes. And we actually don't get very many definitions, and a lot of them are very intuitive, right? Disjoint means they're separate, okay? All you got to do is remember what that means mathematically. The intersection is empty. Okay? So that's, and I'll draw a Venn diagram in a minute, but remember, Venn diagrams, they only help you facilitate writing down a proof. They don't prove anything. Okay, so the second part is that A is equal to A take away B union A intersect B, and if B is a subset of A, the statement becomes A equals B union A take away B. Okay, so let's draw some Venn diagrams that I hope will help clarify the statement. Okay, there's A and B. The union is what? What would I shade to get the union?
All of it.
All of it. It's everything in here, that's in here, or that's in here. Okay? So this is saying that the entire thing is composed of three pieces. Okay, so where is the first piece in this picture?
To the left of the big circle. Right.
Okay, this is A take away B. Right?
Yeah.
Where is the middle piece? Well, it's in the middle. Okay, so. And the other piece?
B take away A.
It's over here, right? So in the picture, it sure appears like it's true, right? At least the first part, that you get the whole thing by taking the union of the blue piece and the green piece and the purple piece, right? What about the second part? Any two of these sets on the right are disjoint. Well, this is where things become tricky with Venn diagrams, because these could be crazy sets. These could be wild fractal sets in the plane or something, right? A and B are just sets. They can be really hard to draw. And so you have this little boundary there, and oh, do they actually meet or not, or what's what, you know? And so that's going to be a little more tricky, but at least it appears in the picture that this is really sort of being cut into pieces. But this is again where Venn diagram, you got to be really careful, okay? It can help you figure things out. It doesn't prove anything. Pictures don't prove things, right? You prove things by using your definitions and your theorems and things you've already proved, and logic. Okay, so since the picture doesn't prove anything, let's go ahead and get started on this. So we're proving this is equal. So again, let's the hypothesis is that A and B are sets. Okay, so we can just forget that. I mean, that's not something we have to worry about. Okay. So we're proving two sets are equal, and usually the best way to do that, not always, but usually the best way to do that is to do what?
Subset in each direction.
Yes, prove left is contained in right and right is contained in left. Okay, that's right. It's like an if and only if statement. It is an if and only if statement, right? It says that X is in here if and only if it's in there. That's what it means for two things to be equal. Okay, so you usually want to split it into two directions. Okay, so let's do this one, and the other direction is going to be an exercise, and so you better pay attention to this direction, okay, and some of the hints that I give you. Okay, keep in mind that when you prove both directions, remember the converse of a statement is different from the statement. It may or may not be true. In this case, they're both true, right, the statement and the converse, because it's equal. But also, the converse of a statement is often, even when you have an if and only if statement, one direction could be very easy and the other direction could be very, 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 very hard. Okay, in fact, it's more often true. I mean, in here, often they'll kind of be, you know, equal hardness going both directions, right? But when you get into more difficult problems in mathematics, it's very often true that one direction is pretty easy and the other direction is really hard. Okay, so, and James is nodding, yeah, he's run into this, okay. So, when I say pay attention to what I'm doing, what I mean by that is pay attention to the ideas about how to structure this and not the exact details, okay. Sometimes you can just run the proof in reverse, but that doesn't always work, okay. So, we're going to prove this direction. The other direction is going to be an exercise, which I have already posted. Okay, so I'm proving this is a subset of that. What is my opening line?
Let X.
Yes, okay, see, I mean, you really, it's amazing how far you can go if you just start with the right place, okay? X an element of A union B. Okay, and what is it we're going to conclude? I won't write it all out because it's complicated, but what am I going to do with X? What do I want to do? I want to show it's over here, right? Okay? That's got to be my conclusion, that it's in here. Now, one of the tricks of the trade when you have an OR statement, and what is that? This is basic union, and that's basically an OR statement, right? When you have an OR statement, so, and again, it's not always true. There are no alwayses in this business, okay? But OR, and you know, put little stars by this if you're struggling with these things, right? OR is often best done with cases. Okay? Because when you have an OR statement, that means one of these is true or the other one is true. And so what you can do is you can pick up each of those cases and run through it and see if you get the right conclusion. You can't do that with an AND statement. With an AND statement, you have these two that are simultaneously true, and you're going to have to use them both as part of your proof. If you pick up one of them, you may not be able to prove anything because you need the other one too. All right? But with an OR statement, break it into cases. That's usually a good idea, and usually the cases are fairly simple. Now, thinking ahead, in your homework, okay, let me write down the cases first, okay? So what are my two cases going to be in this? What are the two possibilities? No and, or, okay, right? So I can start, since it's an OR statement, I can say, suppose X is an element of A. And then I can run with that, right? And then what do I have to do? Even if I reach the proper conclusion, then what? I have to go back and do what?
Suppose X is an element of B.
Yes, and run with that one. Okay, in this case, they're actually basically the same, okay? But let's just start. So those are the two cases. X is an element of A or X is an element of B. Now let's think ahead to your homework. Okay, in your homework, you're going to be going this way. So what's going to happen?
You're going to have three cases?
You're going to have three cases.
3.
X could be in there, or X could be in there, or X could be in there. You pick up each one separately, follow it through, and show that X is in A or X is in B. Okay? Now, we have these cases. Now, to be done, because this is a union, I've got my X now. What can I do with this X in this particular case? To be finished, what do I have to do? Well, we already said we have to show it's in here, okay? But what does it mean to be in here? It's in here, or it's in there, or it's in there. So when I follow this through, I'm good if I can just put it in there, or in there, or in there. All I got to do is, when I'm done with X, it has to be in one of those, right? If it was an AND statement, if these were intersections, then what? I'd have to check that it's in here, and I have to check that it's in here, I have to check that it's in here. But this is a union. So all I got to do is, when I go through, and there are going to be more cases coming up right away, okay, when I got to run through this, I got to just land it in one of those. And then I'm finished. Okay, everybody got that? Okay, so I've got my x. Now let's again look what I'm trying to do. I'm trying to land it in one of these things here. Okay, now what's the difference? It's in A, so we can rule out one already where we're not going to wind up. And where's that? It's not going to be in there. Okay, so now we think, okay, I got to land it in here or I got to land it in here. Well, what's the difference between these two things? We're in A, but what's the difference between this one and that one? In this one, what's true about x? It's not in B. What's true about this one? Okay, that should now already be forming in your mind the next step, two cases. What would those cases be?
X is in B and X is not.
Yes, okay, so either, and I complained about either on some of your papers because either is an exclusive thing, right, in this language, all right? So when you use or, if you put either in front of you, you're saying it's either in this one or in this one, but implicitly not in both, okay? So be careful with your use of either. But here it's okay, because either it's in or it's not. And there's no both. It's not both in or not in, okay? That's one of those, you know, things buried deep in logic that we just assume, right? Okay, so x is an element of B, or x is not an element of B. So now we have an or statement. What do we do with an or statement? We split it into cases, okay? So what do we know now? We know x and element A, we got these two options. Let's run with that one, okay? So now we do another case. Suppose x is an element of B. Now we're still under the case when x is an A. This assumption is going all the way down. So when we say x is an element of B, what do we now have? We have that. And we have that, which puts it in the intersection, okay? So, by definition, since x is an element of A and x is an element of B, x is an element of A intersect B, which is then contained in this monster, A take away B, union A intersect B, union B, take away A. Okay, so this is shorthand here, right? I've said it's in here, but since this is a subset of that, that means that it's in there. Okay? And you know, the amount of detail you give in here will vary. Maybe you would like to write it out more clearly. You might want to say, well, since it's in here, then it's in there, or in there, or in there, therefore it's in the union of those three. I'm perfectly happy if you write this down, okay? That if you find it in one piece, then you say that one piece is a subset of the union of those pieces. Okay? So, the case structure, I'll just write this on the side. The first case is x an element of A, and then we've got two subcases, we'll call them A and B, right? The one we just did was x an element of B. That one's good. Right? The next case we're doing is x is not an element of B, so let's do that. So this is the end of that case. Suppose x is not an element of B, and basically we write the same thing down, okay, by definition. Since x is an element of A and x is not an element of B, x is an element of A take away B, which of course is contained in A take away B, union A intersect B, union B take away A. Okay, and you know, maybe just put some parentheses on there since, okay, but at any rate, that's really the way to make sense of that, okay? I mean, maybe there should be parentheses here if that helps, but okay. Done? Everybody understand why that's done? Okay, and what's case 2? Question? Okay. What's case 2? X an element of B. And now here's where we get to use this lovely word, which will save you a lot of effort, okay? So the proof is similar. Now in this class, you may be tempted to use that when you probably shouldn't. What does similar mean? In this class, similar means you can go back and look at this proof, and if you change the roles of A and B, so this is purely by swapping those letters, then the exact same proof works. Okay? The idea is there's no difference in here. If you look at the statement, there's no difference between A and B except their names, right? A and B are just sets. You don't know anything. Neither one has any properties that the other one doesn't have. So when you go through and look at this, if you take the statement and you swap A and B in the statement, what do you get? You get the same statement, okay? So when that's the case, you can, in a case involving A and B, let's look at what the little A and B cases are going to be here, right? What's this case going to be? X is an element of A, and X is not an element of A. But this argument works if you swap A and B. If that makes you nervous, go ahead and write it out. It's good for you, okay? But on the other hand, don't just say it's similar if it's not, okay? Remember, similar has a very specific meaning, okay? In here, anyway. Later on, mathematicians get a little, similar means maybe not quite so similar. But for you guys, for in this class, and what I'll do, it just means that you can swap the letters and you have the same proof, okay? Questions about that? Does everybody agree that this is done then?
So why is that finished right like that?
Because I showed X is in that, and that's what I had to do.
Wait, so for the B part, it would just be similar to A. Wait,
You mean for the number 2 case?
yeah.
Then you can take this proof and you can replace A by B all the way through it, and you get the same.
A phrase like similarly with the supposition of X being contained in B, if we,
Oh, well, except we don't have any containment like that, okay? I would just say the proof is similar.
Okay.
And be sure that it's right, that it's similar, okay? That's all I'm saying. And if you're nervous about it, like I said, you can always write it down and practice is good. Yes?
I guess what I'm asking is, what is the specific phrasing for saying that the proof for B is similar to?
I would just say the proof is similar. Just at that. But like I said, you better be sure that it really is similar, because if it's not, I'm going to complain about it and, dock points and unpleasant things like that, okay? So it really, and so, your choices are to write it all the way out and then observe that it's similar, right? Well, exactly the same with the letters reversed, or to, to make sure you go through it and see that everything is, it's like symmetry, right? You can replace A by B and everything's the same. Yes?
Would it be alright if you actually wrote out the B is similar to A, just to
Absolutely. I mean, you can write more if you want, right? But
Well, I'm actually asking you if you could do it on the board so I could see it.
Oh.
If that's okay.
yeah, I'm a little worried about time because I want to get to one more thing.
Not like.
Oh, you just the statement?
Yeah, just
okay.
the statement,
Okay.
yeah.
So for I see what you're saying. Yes. For the case X, an element of B, the proof is similar. Okay?
Thank you.
Yep. And it might, often it's useful to write out your case structure, and then you can be very sure about it.
Is there a better word than supposed to? So we have like 2 subcases, 1 and 2.
Yes.
Then the A and B. Is there a better word than suppose?
Well, the reason you use suppose is you're indicating that these are cases,
Right.
and so you're assuming one or the other. You could use assume, but it has to be something pretty close to that, right? Because you're one of those is true. They may not both be true. So you're looking at this one, you're supposing this one is true, or you're assuming it's true. And those words also you should learn to, those words will trigger certain, ways of framing things in your mind when you read them. That's why, we use the word let over and over again. I mean, like I said earlier, math writing and talking can be a little boring because the language itself, because we have certain words that have very, very, very specific meanings, and you have to use those words over and over and over again. And there are only small variations. But the reason is that the reason we use these same words is that it helps you to understand what's happening when you read the proof. Yes.
When we're starting, like say we did want to write out the rest of it instead of saying it's similar, we need to start out with let X is in A union B, or can we go ahead and, since we've already stated that?
No, you've already stated that. So the case structure starts after that.
Just go ahead and
So then you would then start, the next case would start with, so I mean you literally could go through this from here on out and you could just reverse A and B. So it would be, suppose X is an element of B, either X is an element of A or X is not an element of A, right? I mean,
Yeah.
right? And then you have the two cases. Yes.
Asking about the structure for the next.
Right.
I need to go ahead and let, or I can go ahead and suppose X.
Yes, but you don't want to start over with this again because you've now taken this thing and you're working on it. And that's now in the background and you've split into cases and going from there. These are all good questions, and learning how to write mathematics simultaneously will teach you how to think about it. Okay, I need to do one more thing before we go to finish this proof up because the rest of it will be for you. I'm going to look at the second part, and this is one of your homework problems, but I want to look at this statement. Any two of the sets on the right are disjoint. Okay, and there'll be another similar thing there. So I'm going to pick on the first two now. I want to show what is the thing that I want to show. So let me start this somewhere where I won't get you guys mixed up with your notes. Okay. So I'm going to now, for the second part, I want to show that A take away B intersect A intersect B is empty. Okay, I'm showing that these two guys are disjoint. And that means that their intersection is empty. Working with the empty set, what's a good way to approach this? Contradiction. So what am I going to suppose? So contradiction, proof. What am I going to suppose?
An element of A starting with B intersecting with A.
Okay, give it a name.
X.
Yes, suppose, so, okay, so X.
X is an element of A starting with B intersecting with A intersecting with B.
Yes, and then what do I want to do?
That X.
I want to get a contradiction, right?
Yeah.
Okay, now I don't, there's nothing I can do now except,
Prove that X
what?
exists.
No, I want to prove X, I want to get a contradiction now, that X actually doesn't exist. There is no such X. And what's the only thing I can do right now?
Just my definition.
Just write out the definition, okay? So this means what? And let's not do a huge and statement. Let's break it down initially. What's the first place to break it down?
A starting with B.
And X is an element of A intersect B. Okay? Now X an element of A take away B means what? X is an element of A and X is not an element of B. Okay, and X an element of A intersect B means
The next is element of A and element of B.
yep. In other words, right, so we have an and statement there. So what can I gather from this? What's the contradiction? Yes, not an element of B, and X is an element of B, and that's a contradiction. Because that's not possible. Notice that it's sort of like the proof we did over here, but backwards, right? Okay.
Is that the normal symbol for contradiction, the two arrows pointing?
It's my normal symbol. There are other ones, yes, but that's a very and you see why, right? It's two implications butting up against each other. Can't work. Okay? So, or you can just write contradiction, however you'd like to do it. Okay, any more questions about this? All right, we will start with Cartesian products on Monday. Wednesday, the homework will be, we'll do an official claim game, okay? And remember what that means. You need to bring in your worked out solutions and bring